Okay, guys. This is the first question on the review, and I did matching on the review, but on the test, it's actually multiple choice. So what you're going to find is the first thing you got to do when you look at an acid is that you have to realize, is this a binary acid or an oxy acid? And this is a binary acid, and so this is binary because it doesn't have oxygen. This is oxy. This is binary, no oxygen. Sorry. Um, this is oxy. 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 Um, because there's really only three rules. Um, this is binary, and this is oxy. And why that's important is I'm going to come down here and I'm going to give you the rule. And then this is how you name a binary acid. A binary acid does not have oxygen in it. It only has two elements with the exception of HCN. And these are named hydro, stem, ic acid. Because they don't have oxygen, they're things like HCl, HBr, HI, um, H2S, things like this. Um, and their real names are like hydrogen chloride, because I'm going to flip back and forth to the ion sheet here. But if you look, the ones that don't have oxygen, hydrogen bromide, hydrogen chloride, hydrogen fluoride, hydrogen iodide, hydrogen sulfide, polyatomic ions that don't have oxygen in them end with I, with the exception of oxide. Then the ox means oxygen. But look here, acetate has oxygen in it, ATE. Ammonium doesn't have oxygen in it, doesn't end in ATE or ITE. So going back to this, we have three binary acids. This would be called, remember now, hydrostemic acid. This would be called hydrofluoric acid. This is hydrofluoric acid. And so I lost the A, B, C, D, E, F, G because it switched over to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But I'm just going to say this. This would be 9. Oops, I'm trying to write with the mouse, not the pen. That's not good. Okay, grab the pen. Okay, so then I would say that hydrofluoric acid is 9. It's not 9 on your sheet, but you can follow along. I'm just doing the binaries. This would be hydroiodic acid. So this would be 1 or A. And then this binary would be hydrosulfuric acid. Has to start with the hydro. So this would be 3 or C. And now the rest of these are oxy. So what you got to do is you got to go to your ion sheet, Chem 3 edition, and see that this is real name is hydrogen iodate. Iodate, if you look, this is a Chem 3 edition at the bottom. IO3 is iodate. And remember, I ate it. And so this hydrogen iodate, so this would be called no prefix, only binary acids have a prefix. This would be iodic acid. And so this would be 2 or B. This would be, if you look on your ion sheet, this is called hydrogen sulfite. See if you look, where are we? And don't look at the ions that have hydrogen sulfate and hydrogen sulfite. We're just looking at the molecules. So this is SO3 is sulfite, and SO3 minus 2 is sulfite, SO4 minus 2 is sulfate. So when we go back here, and this guy would be called sulfurous acid. And so sulfurous acid is 4. And then this would be, because this is hydrogen sulfite, and ite goes with S, but this is hydrogen sulfate if you look on the ion sheet. And so this is sulfuric acid. On the ion sheet, this would be called hydrogen permanganate. So then this would be no prefix, permanganic acid. So this is 6. On the ion sheet, this would be called hydrogen oxalate. You just use this acid when you did your titration lab. This is not an ion that comes up a lot except for this chapter, but notice C2O4 minus 2 right here, that's oxalate. And so I ate it. So this would be called oxalic acid. So that would be 7 down here. And then working my way down, this would be called hydrogen phosphate. So this would be phosphoric acid. So up here, this would be 8. And then we already did 9. And so then this guy, last but not least, this would be called hydrogen acetate. Again, here's acetate. There's no questions on the test that aren't on the ion sheet. And so this is hydrogen acetate. I ate it. This becomes acetic acid. So that's the nomenclature one. On the test, by the way, if you can't see this, let me just erase it. This is actually a 7 or whatever your letter is. This is multiple choice. So for instance, I will have a question. HF is called, and then there'll be hydrofluoric, fluorous, fluoric, all kinds of weird distractors. So that's question 1. Moving on to question 2. This is the Arrhenius question. And by the way, so Arrhenius defined an acid as anything that starts with H plus. And then a base is anything that ends in OH minus. So we always just cross it off. This is an acid. It's a diprotic acid. So Arrhenius would say that this dissociated into 2 H plus 1s, or you can have plus. Then this other stuff stays together. And here's the crazy part. 2 times positive 1 is positive 2. So this has to be negative 2. Going back to the ion sheet, I keep going back and forth. But again, C2O4 minus 2. Hydrogen oxalate dissociates into hydrogen and oxalate. But I think it's overkill to look at the ion sheet, but you can. All right, so this is a monoprotic acid. So 1 hydrogen comes off. The rest of it stays together, ClO4. And if this is plus 1, this has to be minus 1. If you want to see that on your ion sheet, it's way down here. It's perchlorate, but hydrogen perchlorate, this would be called perchloric acid. This, however, for the first time is a base. And so this is Mrs. Hyde made-up word. I call this dibasic because there's 2 hydroxides. And then this is minus 1. And so then this would be Sr plus 2 because 2 times negative 1 is negative 2. So this has to be plus 2. I think it's overkill, but if you want to see it, Sr plus 2 is right there. This is an acid because it starts with H's. It's a monoprotic acid, so only 1 comes off. The rest of it stays together. If this is plus 1, this is minus 1. Notice up here, fluoride is minus 1. I mean, everything's fitting together. The charges are going to be the same. This is a chem addition, but that's a monoprotic acid, so 1 H comes off, and the BrO3 stays together. It's actually called bromate, which is kind of a cool word if you think of it. Bromate, BrO3 minus 1. This is a base because it doesn't start with H, it ends with OH minus. Always do the acid base part first. Acids make H plus, bases make OH minus. This is K plus 1. Sorry, and you can look on your ion sheet. This is also a base. Why? Because it ends in OH minus. It happens to be dibasic. So let's put 2, and then this charge is 2 times -1 is -2. So the charge on barium has to be +2. And again, you don't really need your ion sheet, but you can use it. Barium is always +2. And then finally, this is a diprotic acid. Again, it's carbonic acid. It's because it's diprotic. 2 H's come off, and then the CO3 stays together, because that's what acids do. The hydrogens come off, the rest of it stays together. 2 times +1 is +2, so this has to be -2. You could also, if you wanted to, look on here and see that carbonate is CO3 -2. All right, next slide, next question. Ooh, I think I put an extra slide in here. Sorry about that. This is the Bronsted-Lowry. So remember, Bronsted-Lowry defined an acid. Acids are proton donors. And when you donate money, your bank account goes down. So from the left to the right, you will see that the H goes down. And bases are proton acceptors. And so you'll see from the right to the left, the hydrogen goes up. And so the key is you have to find this pairs with this, because this has oxygen in it and this has oxygen in it, and this has 1H and this has 2H. 1H, 2H, it went up. That means this is the base and this is the conjugate acid. And then I'm going to quick switch colors. This is the other pair. This started at 1, ended at 0, it went down, so this is the acid and this is the conjugate base. Next thing, this has to pair with this, because a Bronsted-Lowry acid-base pair is identical except for 1 more or 1 less hydrogen. And then the charge goes up or down 1. But this has 1, 2, 3, 4 hydrogen here, and 1, 2, 3 here. It starts at 4, ends at 3, it went down. Acids are donors. Donors go down, and that makes this the conjugate base. And then the other pair is this, because they have hydrogen in it. This has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. It went up, so this is the base. This is the conjugate acid. This has to pair with this, because it's the only thing that has chlorine in it. Starts with 1H, ends with no H's. Starts at 1, ends with 0. It went down. That makes this the acid. And this is the conjugate base. And then this has, these are the only 2 things that have N in it. Oh, I didn't switch color, sorry. Let's go back. This, make sure that we do a different color. This has 3, this has 4. It went up. The thing that goes up is the base. So this is the base. This is the conjugate acid. Okay, I'm going to come over here, push this down. This has to pair with this. It's the only thing that has phosphorus in it. 3, 2, went from 3, ended at 2. The H's went down. Acids are proton donors. Donors go down. This is the conjugate base. And then this, it has to pair with this, because it's the only thing that has carbon in it. Starts at 1, ends at 2. So this is the base. This is the conjugate acid. And then finally, these got a pair, because these are the only thing that has carbon in them. This has 2H, this has 1H, starts at 2, goes to 1, it went down. Acids are donors, donors go down. This is the conjugate base. And then this has to pair. Starts at 2, goes to 3, 2 to 3 goes up. This is the base, this is the conjugate acid. All right, cool, cool. Next question. This is a tough one. And so I'm going to add some slides, but the first one is H is 6.4 times 10 to the -4. So the hydrogen ion concentration is 6.4 times 10 to the -4 molar. I'm just going to go back a slide so that you can 6.4 times 10 to the -4 molar. All right, I know H plus. When you know H plus, the next thing you should get is pH. because H and H, they match. If you're solving for something with a P, you use the log key. So I'm going to do the negative log of 6.4 times 10 to the negative 4. I know that the pH is going to be somewhere between 3 and 4 because 6.4 times 10 to the negative 4 fits between 1 times 10 to the negative 4 and 10 times 10 to the negative 4. But then when you take the opposite, but I'm just going to get my calculator out. Negative log, I'm just punching it in, 6.4, second EE, negative 4. My calculator says 3.19, so the pH is 3.19. And then the pOH is going to be 14.0000 dot 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 minus 3.19. This has infinitely many decimal points. This has 2. If I do 14 minus 3.19, it tells me that the pOH is 10.81. And then if I'm solving for OH minus, this does not start with a P. So I use the 10 caret negative 10.81 key. And then 10 caret negative 10.81. My calculator showing 1.5 times 10 to the negative 11 molar. And then finally, hold on, I'm going to push pause. They want to know if it's acidic or basic, and I always look at the pH. 3.19 is less than 7. So this is acidic. Okay, I am going to push pause just for a minute. Okay, I'm back. So let's minimize this. New slide in here. In the second problem, what they give you is that the OH minus concentration is 0.011 molar. If you know OH, the first thing you got to get is pOH. You're solving for something that starts with the P. You use the log key. You just let the calculator do the work, keeping in mind that if I put this in scientific notation, it would be 1.1 times 10 to the negative 2. And so this pOH had better be between 1 and 2. And when I put that in my calculator, I get 1.96. So that's the pOH. The pH then is 14 exact, minus 1.96, which is 12.04. At this point, I'm going to stop. The pH is bigger than 7. This is basic. And then the last thing we need to find is H plus. And it's not a P, so the formula is using the exponential base 10. So it's 10 to the negative 1.96 power. And if you do that, you get 9.1 times 10 to the negative 3 molar. Whenever you're solving for concentration, you have to have molar or moles per liter because that's concentration units. All right, next slide I'm adding. And the third problem, what you're given is that the pH is 12.23. I'm going to do the pOH first because that's my favorite equation. 14 exact minus 12.23 is 1.77. By the way, the pH is 12.23. That's greater than 7. This one is also basic. Now, I need H plus. Well, I'm solving for something that doesn't have a P in it. So this is 10 to the negative 12.23, which is 5.9 times 10 to the negative 13th molar. And then OH minus is 10 to the negative pOH, so negative 1.77, which is 0.017 molar. Remember, anytime you're solving for concentration, you have to slap molar units on. Last problem in this section. What did they give you? They gave you that the pOH was 8.72. So the pH is going to be 14 exact minus 8.72, infinitely many decimal places, 2 decimal places, I get 2. This is 5.28. And then to get the OH minus concentration, we're solving, this doesn't have a P, so it's 10 carat negative 8.72, which is 1.9 times 10 to the negative 9th molar. And then when I want the H plus concentration, because these two go together and these two go together, it is going to be 10 to the negative 5.28 power, which is, last time I checked, was 5.2 times 10 to the negative 6 molar. And again, go back to pH, 5.28 is less than 7. And so this is acidic. Fabulous. I think that takes care of that chart problem. Classify the following substances as strong acid, strong base, weak acid, weak base, or salt. So this question, I just got to do some review. Remember now, acids, there's 2 kinds of acids. There's binary acids, and there's oxyacids. The rule for binary acids is HI, that's me, HBr, HCl are strong, all other binary acids are weak. So let me just stop. This is a binary acid, no oxygen. It's not HI, it's not HBr, it's not HCl. This is a weak acid. It's an acid, though. It starts with H. This is an acid, but it's an oxyacid. I'm going to come back. This is a base. It doesn't start with H. It ends with OH minus. This is a base. This is neither an acid nor a base. It doesn't start with H plus. It doesn't end with OH minus. This is a salt. Because remember, an acid plus base gives you water, and a salt. This is an acid, but it's an oxyacid. This is a base, because it ends with OH, and this doesn't start with H plus, doesn't end with OH minus. This is a salt. Okay, so now I've done all of the binary acids. Now here's the oxyacid rule. It's very easy. If there's two more oxygen than hydrogen, it's strong. It is strong. If the difference between the oxygen and the hydrogen is less than 2, it's weak. So this is an oxyacid. I got 1 hydrogen, 3 oxygen. Are there 2 more oxygen than hydrogen? Yep, this is a strong acid. This is a weak binary acid. This is a strong oxyacid, but it doesn't matter. It's just acid base. Now, so let me just jump over base. This is an oxyacid, but this is 2 and this is 1. And the rule is there has to be 2 more oxygen. There's only 1. So this is a weak acid. It's actually a weak oxyacid, but it's a weak acid. Okay, now here's the base rule. The base rule is the easiest of all. Strong bases are group, you need a periodic table, group 1 or group 2 hydroxides. So you got to get out a periodic table, and you'll have a periodic table on test day because you're going to need it to do your titration problems. So this is a base. Sodium is in group 1A, so this is a strong base. Copper is not in group 1 or 2, so this is a weak base. Barium is in column 2, so this is a strong base. And that's all I need to say about that one. Okay, so then when you do these pH problems, first of all, I want you to know that there's no such thing as when you have when it doesn't give you H plus or OH minus, but it gives you a formula that has H plus or OH minus in, the first thing you have to do is write the Arrhenius equation. So I'm going to write the Arrhenius equation. This is a base. Bases make hydroxide. It's dibasic, so this makes 2 hydroxide. If this has a -2 charge, then the charge on barium has to be +2. So that's the Arrhenius equation. And then we do a beginning and an end chart, and you either have to put the M here, or you have to put the M on every single number on the chart. So this is 0.0065. The next 3 entries are 0. Here's where life gets interesting. This is a 1-to-1 mole ratio, so this is 0.0065, but this is a 1-to-2 mole ratio, so this is 2 times 0.0065, which is 0.013. Now, that's molar. See, it's over here. Okay, so this is what you know at the end of your BE chart. We know that the hydroxide ion concentration is 0.013 molar. Now, because now we've converted BaOH2 over to OH minus, now you can do, okay, let's get, and it's asking for the pH. So now let's get the pOH first. Now you're solving for something with a P. That means you use the log key. So the negative log of 0.013 is, what do I got? I got 1.89. And remember now, this sig fig stuff is weird. On pH and pOH, only these count as significant. So the pOH is 1.89, but the problem asks for the pH, and so the pH is 14 exact minus 1.89, and my calculator says 12.11. That's the answer to the problem. Now this question is same thing. However, this HBr, and this is an acid, and this is going to dissociate into H plus and Br minus, because acids make H plus, Br minus. Now I'm going to do a BE chart, and I'm not going to put the M's on it. So then you have to go 0.0025 molar, 0 molar, 0 molar, 0 molar, 0.0025 molar. Why? Because this is a 1-to-1 mole ratio. This is also a 1-to-1 mole ratio. I would prefer to not write M 6 times because I hate naked numbers. Okay, I would prefer to just write it twice. So you either have to have the M's here or the M's there. All right, at the end of the BE chart, you know that the H plus concentration is 0.0025. This dissolves and turns into this, so we're in the E row for the ending. And then the problem asked for the pH. And remember, we're starting, whenever you solve for something that starts with a P, it's the negative log. You use the log key. If it starts with P, you use the 10 key if it doesn't start with P. So 0.0025 is 2.60 molar. Oh, that's terrible. It's not a concentration. It's just 2.60. All right. That was bad. This one is a tough one. So let me just say this quickly. You have, oh, actually, I think I changed this. I actually changed this, but I didn't change it here. So lithium hydroxide is what I think I changed it to. Oh, maybe I didn't. I'm looking at the wrong one. Okay, I'm sorry. Hang on. Back up. Let me erase this. So the problem says, and I have this all written up, but this is titration is you put a base with an acid, but we're not going to use the acid nickname. Sulfuric acid, it doesn't start with hydro, so it's an oxyacid. This is hydrogen sulfate. And then this is sodium hydroxide. And I oil it and I get water and sodium sulfate. And then sulfuric acid is H2SO4 because hydrogen is +1, but sulfate is -2, and so you have to crisscross it. And then sodium hydroxide is NaOH, and then water is H2O, and then sodium sulfate is Na2SO4 because sodium is +1 and sulfate is -2. And because of the 2 here, you need a 2 here and a 2 here. And not surprising, this is diprotic, this is monobasic, so you're going to need 2. All right, and so then it says you have 75 mils of a 0.4 mole per liter solution. And the question is, if it's added to 100 mils of sulfuric acid, what's the concentration in mole? I'll do this, moles per liter. I'm going to grab a different color. Keep in mind that this is 0.100 liter because you go 1, 2, 3. And this is 0.0750 liter because you go 1, 2, add a 0, 3. All right, and so now coming down here, we're almost done. Switching to a third color. Here's my U flow. Oops, I didn't want to, I was going to do a different color. Let me switch. Green, this is step 1. This goes in the second set of parentheses. We're going to use the 1 to 2 mole ratio in the third set of parentheses. This goes in the fourth set of parentheses, and this will be flipped. The last thing is always flipped. So here you go, last color, 0.0750 liters of NaOH. There's parenthesis 1. Parenthesis 2 is 0.4 moles of NaOH are dissolved in 1 liter of NaOH solution, and life is great. These cancel. And then you can see from the balanced equation up here that there's 2 moles of NaOH per 1 mole of H2SO4. And now this is crazy. I'm looking for moles on top of liters. I have moles, but I need liters, so I need to do the reciprocal of H2SO4. And notice, this doesn't cancel, moles doesn't cancel, and liters doesn't cancel, and that's good because we want the answer to be moles per liter. Okay, I gotta grab this eraser. This should be more over here. And when I put this in my calculator, you will get, if you round it to 2 sig figs, 0.15 moles per liter. And so this, my people, is the final answer. Okay, I'm really getting tired. We got one more problem to do, so let's go back to blue. All right, so we got lithium hydroxide is the base, and hydroiodic acid, this is a binary acid, so this is hydrogen iodide and lithium hydroxide. And when I oil this, I get water because that's hydrogen hydroxide and lithium iodide. And then hydrogen iodide is HI, like my name, and then lithium hydroxide is LiOH. And these are all +1, -1. Water is H2O, and lithium iodide is L little I for lithium and big I for iodine. And we have okay, so the question is we have 26 mils of 0.25. So this is 26 mils of 0.25 moles per liter. And and this is 0.2 moles per liter. And so we're wondering how many milliliters this will be. And I'm going to change this to 0.0260 liters. And then grabbing green, here's my U flow. This is the first step. This is the second step, the 1 to 1 mole ratio. is the third step, and this is the fourth step. And remember, the fourth step is always inverted. For whatever reason, that always happens. And so we have 0.0260 liters of HI. And then it's 0.25 moles of HI per 1 liter of HI. And then according to the balanced equation, for every 1 mole of HI, you will get 1 mole of lithium hydroxide. And then because moles of lithium hydroxide is on the top, I have to put the 0.2 moles downstairs or it won't cancel. And then 1 liter of lithium, sorry, that was bad. Grab the eraser because I got weird stuff going on here because I have 1 liter and then LiOH also starts with L. And if you do this on your calculator, it says 0.0325 liters of LiOH, but I only get 2 sig figs and it asks for milliliters, so I'm going to go 1, 2, 3, and instead of 32.5, I'm going to write 33 milliliters of LiOH. And then my last problem, just to keep this straight, Arrhenius said an acid is anything that has H plus in the formula. And because when HBr hits water, it turns into H plus and Br minus. A base is anything that has OH minus in the formula. And Bronsted-Lowry said an acid was a proton donor. And they said that a base was a proton acceptor. And that's it.